Hello, everybody. My name is Elijah, and I'm going to talk about how we built an abstraction to enable simple ML operations at Stitch Fix. All right, so what's on the agenda for today? First, I want to talk about Stitch Fix and data science at Stitch Fix. Then I'm going to talk about the problem we solve. Thinking about some common data science workflows and the motivation for making them easier. Next, I want to talk about something at the core of that, which is how we represent a model. Then I want to talk about the capabilities that representation of a model unlocks. And finally, a little bit about where we're going next. If there's one thing I want you to take home, it's that the right abstraction can enable separation of concerns between data science and platform. In this case, it's the abstraction around how we write a model, around how we represent a model, that allows data scientists to focus on writing the best possible model, and platforms to focus on giving them the best possible infrastructure. So, a little bit about me. Grew up in Berkeley, California, studied applied math and computer science at Brown, and then worked at 2 Sigma, a quantitative investment company, and now Stitch Fix, basically on what I studied, on the intersection of software engineering and mathematics, and specifically how to build out software engineering systems that make researchers and data scientists really productive. So what's Stitch Fix and why do we keep showing up at machine learning conferences? Stitch Fix is a personal styling service. There are 2 avenues with which you can sort of interact with the product. Either you get 5 handpicked items by a professional stylist, you keep what you like, and you send back the rest. So it's an iterative process. We have the chance to learn from what you like and what you don't like. Or you can shop at your own personal online curated store. Again, check out what you like, and we can learn from it once you review it and send back information to us. So either way, it's an iterative process in which we get to learn from your preferences. And data science is behind every piece of that puzzle. So there's an algorithms organization, almost 150 data scientists and platform engineers, separated out into 3 main verticals and the data platform. So these verticals are the merchandising and operations algorithm, focusing on optimizing the operations around clothing and merchandise. Client algorithms focus on giving the clients the best possible recommendations, and styling and customer experience algorithms, focusing on optimizing the styling and stylist experience, as well as the customer experience. And all of this is built on top of the team in which I am a part, data platforms. We build tools to make these guys more productive. Kind of blew by the explanation of Stitch Fix, and there's a lot of interesting things to learn, so I highly recommend that if you're more curious, go to the algorithms tour. This is algorithmstour.stitchfix.com, or just Google Stitch Fix algorithms tour. It's a great visualization of how data science is woven into the day-to-day of Stitch Fix and how important it really is to the business. So data science at Stitch Fix, what does the data science organization and sort of the data science day-to-day look like? First, I want to talk about what it's not like and what it's like at a lot of other organizations. So in a typical organization, you might have horizontal teams. These are an engineering team, a data science team, perhaps a data engineering team, each of which is responsible for managing their entire horizontal. You'll have handoffs between them. So if a data scientist wants to get their model into production, they'll write a white paper, get some sort of implementation ideas, and give that over to engineering, who then takes the baton, writes out some code, tests it out, and then works with the data engineering team to get the data they need to run in production. So there's a lot of handoffs between them and a lot of coordination required. At Stitch Fix, we don't do it this way at all. We have a very specific way of managing it that's core to the culture and the way we run data science. So at Stitch Fix, we have a single data science organization that handles all of the data science related questions. We explicitly forbid handoffs. So no one person starts a project and the other person finishes it between functions. Data scientists are empowered to own their projects end to end, from idea to working with the business, to implementation, and then to monitoring and management. We don't want to have anything in their way to get their model out of production. And we have a ton of them. So we really need to build data platform tools that scale to a wide array of problems and a bunch of different data scientists. And it's all built on top of these data platform tools and abstractions. So the goal of data platforms is to make all of these people's lives, all of these data scientists' lives easier, while still allowing them to manage the full stack and to own everything end to end. So what's the problem we're trying to solve, and how does this relate to the sort of organizational structure? Well, the problem comes when you have verticals organized like this. So when we say data scientists are full stack, meaning they are able to own everything, get anything they need out into production, that does not mean that the data scientist builds the stack from the ground up. Again, this is why we have data platforms. And the goal of our team is to scale without more complex infrastructure that data scientists have to manage, and more cognitive burden on these data scientists. So data scientists should always be full stack, as I've been repeating, but can we shorten the stack for them? Can we build a machine learning platform on top of which the data scientists can really easily get their stuff out in production? And that's what we're going to be talking about. So to figure out what this machine learning platform needs to look like, let's take a look at some data science workflows. First, you might think of a data scientist training their model. So they write an ETL, run it on a batch job, then save some model artifact on S3, and then copy it into a production environment. So they have it available for the next step of that process, which is inference. Inference could take a few different forms. This is just a sampling of the types of inference the data scientists do. There's writing the model and running it in a microservice. So serving predictions in real time, running predictions in batch. For instance, getting the recommendations for all clients for analysis or for analysis, and then streaming predictions. So running in based off of streaming features coming in, and then on a Kafka topic, and making predictions on those. And then you got ad hoc or after the fact analysis. So this can involve tracking metrics on those models, evaluating their performance, comparing them with other models, and sharing it with other teams, understanding how your models relate to other teams and how you can sort of work together better. We wanted to enable all of this. There are a few different ways and platforms that I kind of showed to do the inference side, but not much work had been done on the analysis side. It was common to all of data science. So how can we optimize this workflow? And what is the actual problem we're trying to solve? Well, the goal is to build an abstraction to give data scientists all of these capabilities, those black boxes that we just showed, for free. The caveat is that we've got largely uniform workflows. So they all kind of follow that same path of training and analysis, or training and inference and analysis. But the technologies they use are independent from each other. So we don't want to tell a data scientist whether they have to use TensorFlow, scikit-learn, PyStan, PyTorch. They know best, and we trust them to do that. So even though they all write in Python, they can use whatever technologies they want on top of that. And some don't even write in Python. So the question is, what do we put in the middle of this system to make it so they don't actually have to write code to do any of these other capabilities? So they can get them with a little config and the press of a button. All right, I'm just going to tell you what we did, sort of set the scene for the rest of the talk. But the first question is, do we build or do we buy? Hats off to MLflow, TensorFlow Extended, ModelDB. These are all great options. And we actually talked with a few of the creators and really dug into these products to see if they would work for us. Really awesome stuff. And I'm very excited about the direction the industry is going. However, we decided to build our own. Why is that, you might ask? Well, it gave us seamless integration with current infrastructure that we had, which gave us leverage. So one of the hard parts about building these systems is building all of the components. And we had a lot of great components. As I've mentioned, the model lifecycle team, my team, is not the only one in the data platforms team. And each of the pieces of the platform is available and reliable and battle tested. So we got a lot of leverage out of reusing those, rather than pulling in something from the external world and having everybody relearn it. The model tracking and management data model that we use isn't quite standard. We have a lot of different segments and sort of varying ways to slice and dice our models. And we found that open source and sort of commodity-based options were a little more opinionated than we would like about how to organize models. I'll get to what that means in a bit and how we sort of built around that. Having a custom build allowed for pivoting as necessary. So we invested in interface design heavily to allow for plug and play with open source options. So we can sort of quickly iterate, figure out what users need, change our direction as much as we want without vendor lock. But once we figure out something that really works, we can take out some subcomponent of our system and replace it with an open source option. We called what we built the model envelope. The data scientist sticks the model in an envelope, gives it to us, and then we can do anything we want with it. We have all the necessary information. So it looks something like this. The data scientist only writes the training script, and the rest is configuration driven. Here's an example ETL, sort of simplified, but gives a good sense. And you can see the data scientist might load some data, query their features, train their model, and then at the end of it, they tack on a piece that calls into our APIs. So in this case, they save a model and log metrics. We'll go over what all of this means in a little bit. Once they do this, once they save their model, they then send their model in an envelope over to the model envelope registry, where we can give them all of these capabilities. So we're going to talk next about how we represent models in the model envelope registry and what all of these, how we use that representation to unlock all of these capabilities. So first, how we represent a model. All right, I want to compare it to writing a recipe, particularly to think about what information we need to write down a recipe in a way that anybody can use it and cook what you want. So I'm going to propose it's three parts. The first is the instructions. This is how to actually cook it and sort of what to do as you're going along in your meal preparation. Next is the cookware. These are all the sort of like extra bits and pieces that you need the right ones of to make this work. Your oven, your casserole pan, etc. And the ingredients. Without the right ingredients, your recipe is going to be garbage. So you need a way to write it down and communicate it with the readers and cookers of your recipe. And now on to representing a model, and how does this compare? Well, the function, this is what the model does. And that corresponds to the instructions. The context, or the cookware, this is where and how to run a model. And the data is the data the model needs to run on so that it runs effectively and so that we can get good results. So we're going to talk about what each one of these means and how this enables that separation of concerns that I talked about. So the data scientist can focus on giving us the best function, the best context, and the best data, and we can do the rest for them in a way that's self-service to avoid handoffs. So the function, what is this? This is the artifact and the shape. The artifact is a serialized model. This is bytes, including state. So any sort of state or anything that's required for the model to run, and metadata around that serialization. What does this look like? Well, the data scientist passes an object and the platform serializes it. And the platform derives metadata around that serialization. So this is kind of where separation of concerns starts to come in. The data scientist actually just creates a Python object, and we can serialize it for them. They don't have to think about how to serialize it efficiently, how to deserialize it. All they do is pass an object, and we've got it. And the shape. This is the function inputs and the function outputs. So what does this look like? Well, the data scientist can pass us a sample data frame or specify type annotations for a function. In this case, I'm showing the sample data frame, but it's similar with type annotations. You can see they pass an API input and an API output. We can take these and from the shape of these data frames, derive what their function needs to run. So the shape of the inputs. And we then serialize that and represent it in a custom format. So all they have to do is worry about getting us some data and specify the shape of their function, and we can run it, we can store it and use it for later for them. And next, the context. This is the environment of the model and the index, how to look it up. So the environment is composed of a few things. This is the installed packages, so what libraries it needs to run. Custom code, anything that isn't in a sort of published library, but it's code it needs to run. And the language and version. What version of Python or language, other languages if you want, this model needs to run on. So what does this look like? Well, in this case, we do a lot of automatic deriving for them. So with installed packages, we can actually freeze the entire environment, or they can pass pointers if they have a very special case. For instance, if their environment is super cluttered, they can say, we just need these packages, and then we freeze those packages and all of their dependencies. They can pass in custom code as needed, just the pointers to the code, or to the modules, and we can serialize it, zip it up, and make it available for them later. And the language version that's automatically derived, they really never have to tune that. The goal being that their training environment should match their production environment almost exactly. And that's, again, where separation of concerns come in. They are focused on making the best possible training environment, using the right libraries for their model. And we, as platforms, are focused on making that environment available for them in production and in inference. We'll show you how that works in a bit. And the index. This is a set of key value tags, both of which are strings, that form the spine of this envelope registry. It helps sort of look up models. So again, what does this look like? Well, platform derives a set of base tags, and some are required. So every model has instance name, instance description, to help you sort of understand what the model does. And we also derive username and team name from the environment, because we have sort of insight into that in our Stitch Fix workflow system. The data scientist can also pass as many custom tags as they want, and those are used to organize the models, to sort of slice and dice the data. So if they want to say this model is applicable for the women's business line in the US region, and this one's applicable for the men's business line, and then they have a staging and prod one, these tags can help them identify that, and these come into handy later. And then the data. This is the training data and the metrics. So the training data is comprised of features and summary statistics on these features. And what this looks like is that the data scientist can optionally pass a spec that specifies where their features come from for their model. And as they pass data in to specify their API, we use that data again to derive summary statistics on that. So we can sort of understand what the shapes are and what the features are this model were trained on, and sort of the boundaries of those, as well as some different summary statistics. All right, and metrics. These take two forms, scalars and things I like to call fancy metrics, which really are just things that are not scalars. So scalars might be like your validation loss, a number of iterations, whatever a data scientist wants. And fancy metrics have a bigger shape. These could be ROC curves, learning curves, who knows what. It's kind of open and extensible. So what this looks like is that a data scientist logs metrics using a platform metric schema library that we've built. So they can log a scalar, they can log a fancy metric, and we have these validators that ensure that the metric's the right shape. So again, data scientists only have to worry about logging the best metrics to their platform, to the platform, and platforms can help them analyze it and view it and store it, so you don't even have to think about it. So I've talked to you about how we represent a model. Why are we doing it this way, and what capabilities does it unlock? Let's go over a few. First, I want to talk about online inference. The approach that we take is to generate and automatically deploy microservices for a model's prediction. So what does this look like? Well, the data scientist generates and tests out a service locally. So we have a tool to let them run it locally before they put it into production and mess around with some sample results. Then they set up an automatic deployment rule. This is all actually based on tags. So they say when a new model is published that matches this tag, deploy it to this production, this service under this namespace. And they publish the model and then wait for that rule to kick in. Platform runs a cron job. This is a CD system to determine which models should be deployed. Then they generate code to run model microservices. So we actually have a whole code generation system. They can generate a code with a specified config they've given us to serve a model's prediction, And then we deploy that code, the models, with their config to AWS, so they can have it across our whole VPN. Finally, we take responsibility for monitoring and managing the model infrastructure. So we found that this is a system that we build, this is code that we've written, and we get a lot of leverage out of monitoring and managing it. So we actually have hundreds of services that platform monitors, and we control what they look like. So we've built them in a nice, clean way. So they're really not that much work. Okay, so how do we use each piece of this way of writing a recipe? How do we use the function, the context, and the data? Let's go over each one of these. The function. So this is the serialized artifact loaded on service instantiation and called during endpoints. So we can load up their artifact when the service starts and call to it with the data passed in during their in the endpoints. And then we use this function shape to create an open API spec and validate the inputs to push errors upstream. So you can see this is actually a generated service. This is the open API spec. You might be familiar with this UI. There's a query function that takes in the features from the model that we've derived earlier and can validate it. If they give the wrong features, we'll get a 422. So again, separation of concerns. All they have to do is think about giving us the right function and communicating the shape to us in one of the ways we've given them, and we can generate the best service possible for them. How to use the context. As I said earlier, the tag spec is used to automatically deploy whenever a new model is published. Note, the user never actually has to call deploy. It's all done through system managed CD, continuous deployment. So they never have to worry about getting their model out, when to get their model out of production. All they do is save it and perhaps do some messing around with tags. And then we get it out to production for them. And we use the stored package version to build Docker images. The custom code is made accessible in those Docker images for deserialization and execution of the model. So you can see the model envelope and then that JSON config go to the CD system. The Docker image is built, and that's all shipped onto ECS. So their model is out in the microservice serving production results. And finally, the data. So we can use the summary statistics to validate and monitor input to see data drift, to see if their data is different between training and production, which is really valuable to know. And this feature pointer we can use to load the feature data. So you can see there's now a query ID endpoint in which they can pass a client, let's say, and then we load up all the features for that client and pass it into the model and call it for them. Again, that really makes it so they have to worry about less. All they have to worry about is giving us the right features that they use, and we then pull data from the feature store and run it on their model in the most efficient way. Again, separation of concerns. So next capability we want to unlock is batch inference. Our approach is to generate a batch job in the Stitch Fix workflow system, which is built on top of Airflow and Flotilla. Airflow being an open source data orchestration or a workflow orchestration system, and Flotilla is the Stitch Fix job execution environment for running jobs on the cloud. So what does this look like? Data scientists create a config for a batch job, either run locally or run on Spark. There's sort of two modes that they can use. Then they give us a tag query to choose the model. That's part of the config. Say, oh, we want to always run the latest model that matches these set of tags. And they give us inputs and output tables. What data to run the model on and where to save the output to, all within our data warehouse. And then they execute it as part of an ETL. Again, they're full services, their full stack. They manage their own ETLs, so we give them this piece to run as part of it. Platform spins up a Spark cluster, if specified, if they want to use the Spark mode, loads the input data, and optionally joins with features if they've specified a feature table, a feature source, executes the model's predict function over the input, and saves that to the output table. So how do we use each piece of this? How do we use the function, the context, and the data, or all the pieces of a recipe? Well, again, the serialized artifact is loaded on batch job start. So we load it up, deserialize it for them. The function shape is used to validate against the inputs and the outputs. So as we're using Hive as part of the data warehouse, we can validate the schema of Hive against their model shape to make sure their model will work before they even run any code. And we use the Spark function map partitions, as well as PyArrow, the tool for data serialization, to run models that take in pandas data frames, a common pattern in Stitch Fix, efficiently on Spark. I mentioned this to you because it really gets back to that separation of concerns piece. They give us a model And we can figure out how to run it efficiently in batch, which can get kind of confusing and kind of complicated. And how do we use the context? Well, again, we build a Docker image with a frozen package and language versions used to install dependencies and make their custom code available so their model can be serialized with the exact same code on which it was trained. We then use the tags to determine which model to run, as we talked about earlier. And finally, the data. We can use the feature pointer to load feature data if they want to give us a table of IDs instead of a table of features. If they want to give us a table of clients and do some prediction for those clients, we can join that with the feature table they specified for us, or the feature source. And then every time they run as part of our batch job, we store a pointer to the evaluation table they output in the registry. So they can see every run they've ever had and analyze the data. So run the model envelope on the union of feature pointers of the feature IDs in the feature store, and then save that output in our registry. Something they don't even have to worry about. They might not know that it's available, but then they'll look back and debug. We have the output saved for them. So, okay, we've published our recipe. We want to get reviews of it. We want to see how it tastes, what the chef thinks of it. And that's tracking metrics. So how do we do this? Well, the approach is to allow for metrics tracking with tag-based querying. So again, we use these tags as the sort of model spine. It's useful for querying and running models, as well as analyzing metrics. So what do we do? The data scientist logs metrics using the Python client, kind of as I showed before, and explores those in a tool we built called the Model Operations Dashboard. And then they can save a URL from the Model Operations Dashboard for their favorite visualization and share it with their friends or other data scientists. Platform has built and manages this dashboard, and we add fancy new metrics type to those metrics schema libraries. So if data scientist wants to visualize something in a really cool way, we can build it for them, and it's pretty easy. It's a nice extensible system. All right, I want to show you some pictures because I think this is really pretty and I'm really proud of it. Here is what a time series analysis of models might look like. So each one of these dots is a different model, and it's sort of split across different tags. So you're seeing staging versus prod and a few different metrics. And they can see how their models change over time. This is obviously a more contrived example. It's a nice way to demonstrate what the capabilities of the system are. Then they can view their models in a scatter plot. They can view the metrics in a scatter plot. So each one of these dots is a model and a metric, and they can compare sort of two metrics to see how they vary against each other. This is really useful for like hyperparameter tuning or sort of understanding the relationship between hyperparameters and other metrics. And finally, they can save these fancy metrics, CDFs, PDFs, time series RSC curves, learning curves, whatever they want, they can save it and visualize it in our system. So see how across the last few models, these different ones have varied. Happy to answer more questions about this later. There's a lot of stuff I just kind of whizzed by on. So in summation, what was the value added by this platform, specifically by separating concerns? So what is data science concerned with and what are platforms concerned with? Data scientists are concerned with creating the best model, with ensuring they have the model that solves the business problem in the most optimal way. Choosing the best libraries. Again, this is something that we trust them to do. So if they want a version of PyTorch, a version of PyStan, whatever it is, they can choose the best one and understand all the trade-offs. We don't have to worry about that. And determining the right metrics to log. How to understand whether the model is actually performing well in production, or whether the model is actually performing well, and sort of getting the right insight into that. Platform is concerned with making all these deployment contexts really, really easy, so they don't have to worry about it. So they can just press a button. Ensuring that the environment in prod matches the environment in training, so they don't get any surprises when they ship their model out into production. Providing really easy and shareable metrics analysis, and wrapping up complex systems. So they can scale without having to get more and more complex systems that they have to manage. Finally, we're concerned with giving them behind the scenes best practices. So I didn't really mention this, but I think it's a really cool piece of the system where if we find the best way to write a microservice or a really cool new way to run map partitions over with Pyro that makes everything more efficient, we can do that and they won't even know. They might notice that their stuff gets more efficient, but it's really, again, not their concern. So The data scientist focuses on creating the best model, on writing the recipe, and platform focuses on building the optimal self-service infrastructure for them, which is cooking it. Again, it's self-service, so there really aren't handoffs. They manage it the whole way, but it taps into infrastructure that we build to make it really easy and really straightforward for them to do that. So what do we want to do next? A few ideas. We want to go through some more advanced use of the data. So I talked a bit how we use the training data statistics to have visibility into prod training drift. This is really more prototyping our system, and we'd like to invest more in it and sort of understand some good use cases and how this could help data scientists manage their models. We want to build out more deployment context. So I mentioned that people want to predict on streaming and Kafka topics. That currently isn't a capability, although we've prototyped it, and there's been some apps for it, so we'd like to be able to build that out and give that as an offering to data scientists. We want to build out more sophisticated feature tracking and integration. So feature stores are all the rage, and we're starting to dig in and think about what featureization looks like at Stitch Fix. We have some capabilities that I showed to do this, but it's not as sophisticated as we would like. So we're focusing more on building that out. We want to look at Lambda-like architecture. So as I showed you, currently we have a service that we deploy, and that takes a while. So we actually have a system that we query for any model's predictions and get it back instantly. That'd be awesome, but it requires potentially more unified environments. So we might have to have some trade-offs for the data scientists here. We're kind of thinking through options here. I think it's a really interesting problem. And finally, we want to be able to attach external capabilities to replace home-built components of our own system. So as I told you earlier, we invested heavily in interface design in ensuring that the subcomponents each have very defined responsibilities. So that if we have something for them in the outside world that we like, or if we want to give something that we have out to the outside world, that's entirely possible. So if you have any ideas or are interested in anything here, feel free to ask or reach out. Thank you so much. And if you have any questions, feel free to ask me now or reach out later. Really appreciate it. Have a great day.